All right, the second half of chapter 6 is frames and machines. Okay, it's very similar to what we did on the last section with structural analysis in terms of method of joints, in that we look at each piece individually, only now we're looking at each structural piece as opposed to each joint. Okay, this methodology here in general is to find forces, find the forces acting on each joint and support. From there, we're going to apply the equilibrium equations to the free body diagram. And finally, something that may help here is you may be able to separate individual parts of the machine. Okay, this kind of ties together a lot of the stuff we did in chapters 4 and 5 in terms of finding support forces and kind of breaking our systems down into smaller pieces. So we'll go through a couple of examples here. Start with a rather classic simple machine, a pulley, or a pulley system in this case. So we have a fixed ceiling support. We have hanging down from there, we have a pulley. Okay, it's being supported through the center. That connects to a smaller pulley, which is similarly supported. Okay, we have, this will make sense in a moment, hanging below here, a third pulley, which is going to be supported. Now, tied onto the center of this pulley is a cord, which is going to support, which is going to go up here, around and down, around this way, up and over, and then we have a force P pulling on there. Okay, the idea here is this is the same same cord wrapping all the way around here. Attached to the center of this thing, here is a 600 Newton load applied downward on this red pulley here. Okay, the idea here is we can find out what force P it's going to take to support the 600 Newton force thing. Okay, the key here are, again, the free body diagram. Okay, free body diagram of each pulley. Okay, it makes sense to label these. We'll call this pulley A, pulley B, and pulley C. Okay, we're going to assume frictionless pulleys here. Find the tension, and well, I'll give the instructions here. Find tension. In each cable. And force P for equilibrium. Okay, it almost doesn't matter what they're asking. A problem like this, you're going to split it into each piece and draw the free body diagrams. So I'll go ahead with that. So for pulley A, Okay, we're going to have support up here, call that the reaction force, that's the one hanging from the ceiling, call that R. We have force P pulling down on this edge from this on this edge here. We have force P also pulling over here. Again, this same cord all the way through here is going to have tension P all the way through. So we have P pulling down here and P pulling down here. We also have applied at the center the tension in the cord that connects it to pulley B. Okay. So we've got 4 forces acting on there, the support force attaching it to the ceiling, the cord attaching a tension in the cord connecting it to pulley B, and then 2 points of contact with the long cable with tension P throughout. Okay. So then we're going to have, so this is pulley A, pulley B. Okay. This one has this cable tension extending upward. Again, the cable connecting A and B is going to act upward on B. We also have force P downward here and force P downward there. Okay, this allows us to take a look at, to analyze this one. And then finally, pulley C is going to have more going on here. We have attached to the center, we have force P pulling up here. We have force P pulling up here. It should be straight up and down. I'm just having a problem with the arc. Force P over on this side, and then we have 600 newtons down. Okay, so here we have 1, 2, 3 points where this longer cable with tension P is connected, and then we have the 600 newtons hanging downward. Again, we're assuming all these weights are frictionless and at the end of negligible weight. So this allows us to take a look at this. And now we're going to do, again, apply the equilibrium equations to each of these 3 pulleys. Again, to solve for each of the 3, again, each cable and force P for equilibrium. So we have force, the cable here, which we call force R, the reaction force from the ceiling. We have tension in this cable here, which we call force T. And we have force P, that tension, again, it is tension in this cable all the way through, but it's because of the applied force here that keeps that tension. Okay, so we need to go through and analyze and find out what these are. I'm going to take down the main drawing. Put that back up once we're done with the analysis a little bit here. Okay, so in all 3 cases, we have summation forces X, summation forces Y, and summation moments all have to equal 0. Summation forces X is going to be meaningless in all 3 cases. None of them have any applied, none of them have any forces acting in the X direction. Okay, summation of moments, didn't give you diameter on any of these pulleys, so finding moments is going to be tricky. We may have to resort to that, but if we're lucky, we might be able to do this simply with summation of forces in the Y. All right, to do that, well, here summation of forces in the Y are P, T, and R. Too many unknowns. Here P and T, 2 unknowns. We could do that with moment. If we could work with summation forces Y and moment, we'd have 2 equations, 2 unknown. But at point C, we have the 600 Newton force and 3 values for P. That's only 1 unknown, so we can do that. Summation of forces. So for pulley C, summation of forces in the Y equals 0 equals 3P minus 600. This gives us 3P equals 600, and then obviously P equals 200 newtons. Okay, so now we know P. We can go back, look at pulley B here. Summation of forces in the Y equals 0. Here is equal to T minus 2P. So this gives us 0 equals T minus 2 times 200. T ends up equaling 400 newtons. Okay, so we have a 400 Newton force connecting A and B. And then at pulley A, we can go and find force R. Summation of forces in Y equals 0 equals R minus 2P minus T. Okay, R upward, 2P and T going downward. So 0 equals R minus 2 times 200 minus 400 means R equals 800 newtons. Okay, if I go back and draw my and re-examine my entire system here, it ends up looking like oops. Connected that to the wrong edge. That goes there. And pretend those two are vertical. And we're going to have our 600 Newton load here. And we found that our force P applied at the bottom was 200 newtons. Okay, this allows us to say that the tension here throughout this whole system is 200. So this 600 Newton force is being held up by three 200 Newton forces. Okay, this has two 200 Newton forces pulling down, which allows 400 here. This has two 200s and a 400, which means it's supported by the 800 force we found here. We can also look at the entire system here. Within the system, we have a 200 and a 600 pulling down. Our support force at the top is 800. That makes sense as well. Okay, so this is a simple example using a pulley system here. And as you might expect from a pulley system, well, this pulley system, we pull with downward with 200 newtons, we lift a force of 600 newtons, which is what we'd expect from a simple machine. Okay. Move on to another example here. We take a look at one that's a little bit more familiar to what we've been doing in terms of our structural elements. We'll have a wall on the side here. Okay, we're going to have two pin joints, one here, and that's going to attach to a beam that sticks straight out. Okay, we're going to have, and at the end of this beam, we'll get to that in a second, we're going to have another pin joint here. This one we're going to have a beam that goes up to here. I'm going to draw that a little straighter. Where's this thing? All right, we're going to have a pin joint connecting the two. And then this one has to extend a little bit further. And it has a pulley on the end of it. Okay. Up and over this pulley. We have a weight hanging that is 80 kilograms. All right. Given that, we'll go with some geometry here. This is going to be 0.5 meters. We have a length of 1 meter here. We have a length of 0.7 meters here. Drawing is clearly not to scale. And we have a diameter on the pulley. So we have a radius of the pulley of 0.1 meters. All right. And we're going to find I'm going to label 3 points here, A, B, and C, and that's what we're going to find. Okay, so finding forces at A, B, and C. So we need to break this up into pieces. We're going to have at least 2 pieces here. It makes sense to keep, considering we don't care about the forces between beam BC and the pulley, we're going to keep those attached. And then we're going to look at this beam here as well. Okay, so I'm going to draw those 2 beams and I'm going to draw the free body diagrams for them. So taking a look at beam AC, we have draw that a little bit near. Apparently means narrower, but that's fine. So at A, we're going to have support forces, AY and AX from the pin joint here. At point C, we're also going to have supports from the pin joint, CY and CX. And then at the end here, we're going to have this force pulling upward from the cable. That cable, well, this is going to be a weight. (80 times 9.8). That ends up resolving to be a, I should be able to do this in my head, 784, not 764, sorry. 784 newtons. So that force gets transferred right back over here, so we know this is 784 newtons. Okay. All right, I'm going to label that on the inside so you guys can definitely see it. Okay. The other beam we care about is beam BC. And I'm going to erase this so I have some room to draw. Beam BC. This one I'm going to include the pulley on the end of it because that's if I separate the pulley from the beam, I have to find all the reaction forces between the pulley and the beam, and I'd rather avoid doing that, so we'll leave that out. Okay. Here we have pin joint at point B, BY, BX. Okay, point C, this is an important detail. Here, we assume the forces were up and to the right, the forces acting on beam AC. Okay, because of Newton's third law, the force that acts in one direction on one object, that pushes back equal and opposite on the other object. That means we have to draw the forces on beam BC in the opposite direction. So here we're saying beam BC pushes on, all right, at point C we have interaction between beam AC and beam BC, between the horizontal beam and the angled beam. Okay, we're saying the angled beam pushes on the horizontal beam up and to the right. That may not necessarily be true, we're just assuming that for now. If it comes out negative, we know to flip the direction of the arrow, it doesn't matter in the long term. But we need to pick a direction on our diagram. So when I drew beam AC, the horizontal beam, I assumed it was being pushed up and to the right. That means it's pushing down and to the left on beam BC. Okay? So anytime you have the interaction between 2 objects, the support forces on one get drawn in the opposite direction on the other. So when I draw this, I'm going to go CY and CX. Okay? This means the vertical beam pushes on this up and to the right, the horizontal beam pushes on this down and to the left. When we attach them together, the X forces cancel, the Y forces cancel, we end up with no net force on our entire structure. But within the internal interaction between these two, we have to have them in opposite directions. So we'll move forward from there. We also have two forces acting here. We have 784 here, and we have the same 784 here. Okay. So this one gets a little bit trickier. I'm going to take the diagram down. I'll put it back in a bit when I want to analyze individual pieces. But the problem told us to find the reaction forces at points A, B, and C. Once we find those, we will be able to say we've solved the problem in the end. So both of these problems we are going to, I'm going to move this one over a bit so I can kind of work in two columns. Made a mistake. I warned you not to. Cx, Cy, 784 newtons and 784 newtons. All right. So in all of these, we have summation of forces in the x and the y and summation of moments. So what we're going to do here is start looking around, find places where we can actually solve these things. We're probably going to end up using all of these relationships. We do have 6 unknowns. We have AY and AX, BY and BX, and CY and CX. So we need to find all of those. We can work through this step by step and hopefully get them without doing too much simultaneous equations. So we can take summation of forces, summation moments. Summation forces in the x, we've got 2 terms here, 2 terms here, can't work, can't solve for anything. Summation forces y, 2 unknowns here, 2 unknowns here. Again, can't work with anything there. Summation of moments. Now we're looking for things that can help us out and get things to drop out. Well, I'd like to work with this one because I don't want to have to deal with moments on an angle. So I'm going to try and do summation of moments here. If I take summation of moments about point A, I end up with, and remembering the geometry, this is 1 meter. It's 0.7 meters. Okay, that is, yes, okay. That's 0.7 meters. So summation of moment about point A, we have AY and AX have no moment on them, they drop out. CX is pulling directly away from A, it has no component. So we just have a moment due to CY and the 784. So this equals 0, this equals CY is going clockwise, so it's CY times 1 meter plus 784 newtons times, that moment arm is 1.7 meters. Oops. Okay, so this ends up like this. We end up with CY equaling 1332.8 negative newtons. Okay, so CY in this diagram is actually pushing downward, and CY in this diagram is actually pushing upwards. Okay, if you'd like to change it around, that's fine. But I do need, we just need to note that it is CY is negative compared to the way we drew this. All right. Now from here we have enough to be able to solve for AY. Okay, getting AY here, we can do summation of forces in the Y. We could go and take moment about C if we wanted to, but summation of forces in the Y works too. Equals 0 equals AY plus CY plus 784. Okay, so we have 0 equals AY plus CY is our negative 1332.8 plus 784. This gives us the AY. This one is also going to be in the, oh sorry, it's going to end up being positive. is 548 we need. Okay, so AY is upward. AX and CX, we don't have any means to solve. Okay, summation of moment about any point on this beam is going to drop those out. Summation of some forces in the X is just going to tell us that they're equal and opposite, which is useful, but not going to give us an answer until we know one or the other. So now we need to come over and look at this one. Okay. So in this beam, we have BY, BX, CY, CX. We found CY. Check that off. But we still don't have any of the others. Well, we can find BY just using summation of forces in the Y. Summation of forces in the Y equals 0 equals BY minus CY minus 784 minus 784. Okay, kind of a big mess, but it works. So we have 0 equals BY minus, again, I haven't changed the drawing, so I keep the sign, minus a negative 1332.8 newtons. I'll leave units out for now. Minus 784 minus 784. Solve this. BY ends up ends up 235.2. And that newtons, obviously. Okay, so now we know BY. So for the whole system, we're able to identify all of the vertical forces. What we're left with is BX, AX, CX, the three X component forces. Those are a little trickier here. We're out of summation of forces solutions here. We do have to do a summation of moment about this on this piece in order to solve that. So looking at some of the geometry here. Okay, this distance was 0.7 meters. This distance was 1 meter. And then the radius here was 0.1 each step of the way. Okay. Okay, so in case this doesn't come out on the screen, between B and C, there's a horizontal distance of 1 meter. Between C and the front edge of the pulley is a distance of 0.7 meters. The radius of the pulley, i.e. front edge to center and then center to back edge, is 0.1 meters each. So that allows us to go ahead and calculate moment for some of these. So I'm going to take what seems to me to make the most sense, summation of moment about B. Summation of moment about B. Okay. The Y components here are going to be fairly easy. So we have a moment about B for CY is going to go clockwise, so that's minus CY times, well, the whole thing equals 0, obviously. Minus CY times 1 minus 784 times 1.7 minus, for the other 784, times 1.7 plus 0.1 plus 0.1, 1.9. We have one other piece here. We have this CX. This is going to be around here. Plus CX times that moment arm. That moment arm is going to be, okay, if you remember the geometry from the original picture, we had C was along the line attaching it to the wall. This distance was 0.5 meters. So this is 0.5. Okay, so we have 0 equals minus CY was a negative 1332.8 times 1 minus 784 times 1.7 minus 784 times 1.9 plus Cx times 0.5. Okay, you guys can all do the algebra there. That gives us a Cx value of, it's positive, so $279.2. Okay, and that's a Cx. All right, so now at this point we've solved for 4 of them. I'm going to kind of clean this up a little bit. Cx was found to be 2979.2 newtons. So now I can take this down. Okay, we can get Bx quite easily here. Summation of forces in the x equals 0 equals Bx minus Cx. So that means Bx equals Cx equals 2979.2 newtons. Okay, so these are actually pushing in the correct direction. Cx was drawn in the correct direction. It's pushing to the left on this beam and to the right on this one. So we now know both components at B, both components at C, and we just need the other one at A here. Summation of forces in the x direction equals 0. In this case we have AX plus CX, the way I've drawn it. So we have 0 equals AX plus CX is 2979.2. This gives us that AX, as we've drawn it, is a negative 2979.2. Okay, so I'm going to redraw my original picture here. Forget the artwork for now. Make that a little bigger. Okay, so what we found is that point A, we assumed it was pulling to the right, the pin joint had to push to the right and up. As it turns out, it's pulling to the left and up. That makes sense. This pin joint is pulling it this direction, okay, keeping it from falling this way. That makes sense. Point B, okay, again, we drew it to the right and up. As it turns out, that's correct. It's pushing it to the right and upward, so it's supporting it in this direction. Point C, okay, we assumed that the angled beam was going to be pushing the vertical beam up and to the right. As it turns out, it's pushing Cx. It is holding it to the right, okay? It is pushing in this direction, which makes sense considering this is trying to pull this direction. And it's also holding it up slightly with a 235.2 Newton force. So it's actually pushing up into the right on that one as well. Okay, so we did end up, C. So it ends up pulling downward on the horizontal beam, which does make sense as we're pulling this way, and the x component is pushing to the right, which does make sense. Okay, so all these do work in terms of what our structure actually looks like in terms of keeping things in equilibrium. So this is the basic approach to handling frames and machines. You're going to have structures of multiple elements that are attached together in various ways. Simply a matter of finding what forces, starting with the free body diagrams, combining things similar to what we did with Chapter 5 with equilibrium of rigid body, except now several of our rigid body structures are going to be interacting with each other. The key to that is the Newton's second law rule, making sure you keep your arrows and your force signs correct.